So today's video is going to be a follow-up on the previous video I made about short circuits and the device that I made in that video to measure short circuits. In the comments of the previous video, one of my subscribers, whose YouTube name is T1D100, suggested that I could make a millivolt to volt adapter using an op-amp and therefore use a multimeter which didn't have a good millivolt range. He sent me a schematic of a circuit that he had used himself, and I will show that to you now. So here's the schematic he sent me. It's using an MCP602 op-amp to take the input from a millivolt source and convert it to a volt source. Notably, it has a selection switch here to change the gain. I believe this is probably from 100 times to 10 times potentially. So I kind of thought about this and I thought, well, if I'm going to go ahead and come up with an alternative solution, it would have to be based on cost. I'd like to keep the cost as low as possible. So I then went down the path of, well, what happens if I can use a very inexpensive voltage meter instead of the multimeter? That way I can keep the extra costs of adding the op-amp and the extra circuitry down by replacing a multimeter with a very small voltage meter. I'll show you what I mean in a minute. But with that in mind, the biggest problem with the circuit that was sent by T1D100 is that this is actually an inverting amplifier, and therefore the output is actually negative. And the meters that I was looking at using do not measure negative voltages, they only measure positive voltages. So with that in mind, I thought, okay, well, can I modify this circuit? Can I keep to one op-amp? It's a dual op-amp, and use one of the stages of the op-amp as a unity gain inverting amplifier to keep the output positive. So I kind of have a bit of a think about that, and I came up with a circuit. This is the circuit that I came up with, and it's based on the one that I was sent by T1D100. So if we look into this, we have 3 input resistors which give a multiplication factor of 1, 10 and 100. We take the first stage of the op-amp as an inverting amplifier with the gain determined here, and the output of that is then fed into the second amplifier, which is again an inverting amplifier with unity gain, so it will invert the voltage. At this point it's a negative voltage, and then at this point it's a positive voltage, and then we use a simple voltage meter to measure the output voltage from the second stage of the op-amp. The only major drawback of this design is that the voltage meter does actually need a higher voltage supply. I still want to have 4.5 volts on the LM317T, the original circuit, which is obviously feeding between this point here and then one of the 3 inputs depending on the scale that you want. The voltage meter does need a higher voltage than that to be accurate, typically 9 volts. I think it does probably work off 5 minimum, but I found it's very inaccurate at that, or at least the ones that I have. It's much happier running at 9 volts. As far as cost goes, the MCP602 I paid 54 pence for. The digital voltage meter I actually got in a pack of 4, cost me £1.90 or £1.80, so around 45 pence each. I've got 8 resistors in the circuit which I priced at 5 pence each. Breadboard, extra battery, other connectors, etc. I've got down as 235. That price may be a little on the low side, but we'll go with it for now. That gives me a total of £3.79. So this is one of the meters and a 3-digit 7-segment display. It's just a 3-wire device. This came in a pack of 4 and they were £1.89. So here are the components I need to make that circuit. I've got 5 10k resistors, I've got one 100k resistor and 2 1 meg resistors. I've got the voltage meter, MCP 602, small breadboard, and a couple of batteries and some test probes. So we can go ahead and start making the circuit. So I'll start by putting the MCP 602 into the breadboard. And then the diagram here so I get the numbers right. So we'll start with R4 and R5. So that's going from the positive side to 1 pin location, and then negative side to the same row. Okay, and then my first jumper is going to go between that point, pin 3, which we will do like that. Okay, so next I'm going to put in the feedback resistor, which is a 1 meg resistor, and that goes between pins 1 and 2. Oops. Wow, fiddle. Okay, I'm putting those over this side so I can still get access to the chip should I need to get the meter probes and stuff on there, so I want to try and leave that as open as I can for now anyway. Okay, next we'll actually take the output and we'll feed that to a pin over this side, just a blank one. Then I can get a 10k resistor, so this is R7 on the circuit diagram. And then we can feed that into pin 6. And then we've got another 10k for the feedback resistor on the second half. On the second stage, so that's going between pin 7 and 6. Okay, that's my feedback for the inverter. Okay, then next up we've just got the 3 input resistors, so I'll just that'll do for testing. So I've got the 10k on 23, the 100k on 24 and the 1 meg on 25, so that's R1, 2 and 3 on the schematic. So then we can take the output of those, which is row 19, and then we can feed that to the input, which is pin 2. So we'll go to pin 2, like that. Then we need to connect pin 5 and we need to take that over to pin 3. So pin 8 is positive and pin 4 is negative. Okay. Right, so then we have the voltage meter. So the sense wire for the voltage meter is the white one. And so it's going to pin 7. And the supply, so the ground is going to go to effectively, which is pin 3, or the center point of the 2 resistors there, and then power for that we can bring over to here as a separate power source for the meter. That doesn't work very well until it really gets up to 6 volts or so, so I'm going to run that from a 9-volt battery for testing, which I have right here. So let's connect the 9-volt battery. So that's going to go to the common ground point, and then to the positive for the meter. So we'll just try that. Connect the 9-volt supply. Meter's on, that's a good start. Then the power for the op amp itself. So the power for the op amp is going to go in here. It's a bit loose, hopefully that'll work. Right. Okay. I'm just going to zoom out a little bit. Okay, just do a quick couple of voltage checks to make sure that we've got some correct voltage going on. So the op amp itself should have 4.5. Turn it on, maybe help. Okay, 4.5 on the op amp, and pin 3 should be half of that, 2.2. Good. Okay, that's a good start. And the voltage meter saying 0, which is good. Now we need to introduce some millivolts into the circuit, and then we can see what output we get. So I shall just set that up and I'll be back in a moment. So I've added the LM317 circuit with the potentiometer as I had it set up in the last video, so we can adjust the output current. So we'll set that for 50 milliamps or thereabouts. that's set for 67. I think that's close enough. So now I'll attach some probes. And the output to the input, so we'll go with the times 100 input first, and we can see that we have full deflection on the meter, which is good. So just so I can test and set this up, I'm going to use some crocodile clips or alligator clips, depending on where you come from, just to clip a strip of nickel to the end of the test leads. Okay, so we have something happening, that's good. Okay, I've got 16 millivolts coming in, which is equating to 1.5 volts coming out. That's better. See if I can set this up so you guys can see it. 16 millivolts coming in from the probes, and we can see that the output is 1.5, and that's on the times 100 input. If so I've adjusted it now, so I've got 29 millivolts coming in, and I've actually got 300 coming out, but this meter just doesn't work very well below 400 millivolts. And I've cranked the power up, and we can now see that we've got 93 millivolts coming in, about 1 volt coming out. And you can see that it's measuring 1 volt, and that's on the times 10 range. And I've turned the output of the 317 down to minimum, so now we have coming in 9 millivolts and coming out about 1 volt, and that's on the times 100 range. So I think that's proof of concept. So now I'm going to transfer this circuit onto a piece of prototype board using my spot face cutter. Thanks to Mike Panchord. Hope I got the name there right, Mike, who correctly identified this tool for me in a comment on the last video. Thanks, Mike. So let's go ahead and start transposing this circuit onto the Breadboard. I'll start with a IC socket. Not sure if this is actually going to be big enough, this piece of Breadboard. No, I think I'll get a bigger piece. Hang on. I found one of these pieces of Breadboard that have lots of stuff marked out on them already. I think this should be quite useful, quite good for this circuit. So I'm going to go ahead and use a piece of this and we'll see how it works out. So I'll start by mounting the board in my PCB holding gadget here. Okay, so I'll give myself plenty of room. So we'll start. Yeah, it's not exactly ideal, is it? Because I don't know if you can see that it's not very well centered around the spaces. Anyway, we'll go with that. I'll have more on that side, I think. No, we'll have more on that side. Okay, so I'm going to pop that in right there. Okay, so I'm just going to take the components straight off the breadboard as I use them. Let's take out all these jumpers. Okay, we'll start with the 3 input resistors. I think we'll just pop those out of the way. Over here. Solder those in. Okay, so I've got my 3 input lines there. I'm going to use this. I'm going to use this central line here as my reference point. So I'll have that one that side. That can be the positive, and we'll have that one. Side, that can be the ground. Okay. We'll put in the feedback resistor for the first stage, which is on the schematic R6. That's a 1 meg resistor. And while I'm here, I'll do the other feedback resistor on the other half, and that is between pin 7 and pin 6. And then we've got the input resistor, which basically is linking the output of the first stage to the input of the second stage. So that's going to go from pin 1 to pin 6. to get some jumper links now. So I'll just pull off a section of that. So the first link I want to do is from pin, this one, which is pin 1. And I'll jump over the board. To go to pin 6, which is that one. Okay, so that's taken the signal out pin 1 through a 10k resistor across the board into pin 6. We need to jump to the input, so I'm actually going to use a jumper for that, because it will make it a lot easier for me to change the position should I need to. Okay, so that's our input. Now we can go what's my piece of wire? There it is. We can go from the common, virtual common, which is basically the junction of R4 and R5, to pin 3. And we also need to do the same with pin 5. And I'm going to connect just a couple of these jumper wires for the power. Okay, so that's the power for the op amp. I use the orange wire for power for the screen, for the meter. We'll have the white wire, which is the output voltage, pin 7, to the meter. Okay, I now need to connect a power and ground for the op amp itself, so I'll go ahead and do that. Let's just check continuity. So ground to pin 4, supply to pin 8. We should have 10k between ground and that point and positive and that point. That's good. 10k between 6 and 7. 1 meg between 1 and 2, and then 10k between 1 and 6. Okay, I think that's good. So there's a couple more things I need to do. I need to connect some power for the meter, and that will be blast. We'll do that again. Then we need to connect the negative of the battery to the common. So we should just be able to do that with a blob of solder, I hope. Like that. Yep, that's good. Okay, just let me check continuity of that. Should effectively be pin 3 to there. Yes, good. Okay, so let's connect the probes. So the ground can go anywhere on there. The positive probe then goes to the input. What I've decided to do is just to put a pin header, and then I can just put the probe into the one that I need. So that should go, hopefully, there. Yes, that should line up with all 3 of my input resistors. And then I can simply plug that into whichever one I need for testing purposes anyway. So I can go ahead now and connect the meter, I think. So output, I'll just actually jump that over to there. So output is the white one. Black one goes to our virtual ground. third one goes to power. Okay, that's the meter. So it just leaves the LM317 source to connect now. So I'm going to use this pre-made PCB just for ease of use. So again, ground is going into our ground. Power. And the output. And that will have to go in the same pin as that. Maybe I will attach those two together. A moment. Okay, so let's take it out of there. Let's put the op amp in. Get rid of that and get rid of that. Okay, I'm just going to have a tidy up. I'll be back in a moment. Right, so I've had a bit of a tidy up. And I think I'll start by, I need to set my current. So if I connect, my 9-volt battery is actually dead. So I've just got two lithium batteries in here in series. It's about 8.2 volts-ish. So we'll just use that for now. Right, so let's set the current. So if I just short circuit across those two there with my meter. So we've got 17 milliamps at the moment. We'll crank that up to about 50. So next I need to power the op amp. So I've got my 4.5 volt battery pack here. So I'm just going to tag those wires onto there. That will do for now. Okay. Right, so let's reconnect the meter. Let's switch the op amp on. I'll just check the voltage input to the op amp. 4.4. So this is my input from the probe, so I'll put that to the times 100 input, so that should go full range, yes. Right, let's get a piece of strip. Okay, so that's given me 1.3. You guys can't actually see that. Right, I'll just get my lens out here so you guys can see. That's better. Okay, so from one end of the strip to the other we've got 1.48. Let's get a thinner strip. Let's try that. This is some lower resistance. Okay, that's going off scale. Okay, something's not quite right. I'll be back in a moment. Okay, no, I think it is working. So across the bigger strip here, we've got 1.48, which should be equivalent. I'm on the times 100 scale, so that should be 14.8 millivolts. Across this one, across the smaller strip, it actually goes out of range. That's because we're actually higher. So if I move that into the times 10 range, and now we get, if I make a good connection, and now we get about 140, 130, 140 milliamps, and that's on the times 10 scale. So we can just verify that by using the clips. So if I actually clip the larger piece in, so input we've actually got, yeah, we've got 14 milliamps. So if we put that onto the times 100 scale, we've got 14 milliamps times 100, which gives me, sorry, millivolts. We've got 14 millivolts times 100, which gives me 1.4 volts. And then I'll clip in the smaller piece. So that's given me 17 millivolts. 17 millivolts has given me 1.67 volts output. If I actually turn the current down, and we can measure the input voltage, it's coming in at 10, 11 millivolts, output 1 volt. So it's actually working quite well. Let's find something of a slightly higher resistance. Back in a moment. Found a piece of solder here. So that's given me just over 20 millivolts. So if I go up the scale, 21 millivolts again. This meter just doesn't work. This voltage meter just doesn't work very well at lower voltages. I've basically got 200 millivolts coming out. So I've got 20 millivolts going in, and then coming out I've got 220, so it's on the times 10 scale, but this meter just doesn't work well at lower voltages, but anything below about 0.3 it doesn't work. So I think in the times 100 mode it works very well. In the times 10 mode, because this meter doesn't work well below about 300 millivolts input, we've really got to get up to about 30 millivolts input before it really starts working as you would expect. But that is just the flaw of this digital voltmeter. The actual output is working fine, so the circuit itself is working very well, but we do need to make an improvement onto this small voltmeter here for it to work through a decent range of operation. Although I think the 2 to 20 millivolt scale is probably adequate for the purpose of the original scope of the device. I think on the original test from the last video, if I remember correctly, I had a 1 millivolt difference between, I've lost the thin piece of nickel. I had a 1 millivolt difference between the thick piece of nickel and the thin piece of nickel. So that should equate to 100. So we've got 0.74 and 1.2. So it's actually measuring a better difference between the two. But I've probably got the current set much higher, have I? Let's just check the current. I think I had 50 milliamps set on the original. Oh, 30. Let's put that up to 50. Okay, 50 milliamps. Then we'll go. Okay, so we've got 1.25, so it's 12 millivolts, and oh yeah, that goes off scale. That's why I turned it down. I remember now. Yeah. Yeah, that's a scaling problem. So let's set the current to 40 milliamps. Okay, 50. Let's try 40. Okay, 39.7. And then with the test probes on the fat piece. Okay, we've got 0.97, and on the thinner piece yeah, we've got 119. So that does work well. Setting of the test current is more critical with this setup because we need to have we've got quite a small range of operation due to the circuit design and the fact that this small voltage meter here does not work well below about 300 millivolts. Other than that, it's working quite well. So I have just found an alternative meter here. Now this one also has a current display on it. So although this is a little more expensive, I don't really know how much I paid for this. I'll check that. I'm going to put this into the circuit and see how this one compares. So we can go ahead and connect this one up. Yeah, it's not quite so easy. Let's try and tack that onto there also. Okay, not quite as neat as it could be, but it is just for testing. Right, power to the meter, current to the meter. Let's just try powering it up first. And the other way up now. I hope you can see those. Yes, you can. Right, so I'm going to put the input into the times 100. Yeah, that's come out. Okay, I'll have to resolder that. Right, one tick. It's reattached. Right, so the meters are actually working. Now that's telling me that I've got 40 milliamps, but I don't know why, because I shouldn't have 40 milliamps. Unless those are shorted together. Okay, I think I've made a mistake. I'll be back in a moment. Yeah, of course, I am an idiot. I need to put a switch in series. This meter has a current shunt on there, which is obviously going to put a short circuit on the load. So I need to put a switch on there to test the current. So we'll just take a push button switch. Solder that in series with the ground wire. Let's turn the power off. Connect that to ground. Okay, let's have another go at that. And no, I'm still saying it's 40 milliamps. That's peculiar. I got short. Yeah, I've still got a short. Why is that? Beep, please. Thank you. So there can be only one possibility, and that is, yeah, okay. I need to put the switch in the positive side. I've connected the switch into the positive side now. So let's just have a bit of a tidy up here. Yeah, I think you can just about see there. Maybe put a wedge under there. Is that better? Yeah. Right, now. So if I short the test probes and press the button. Okay, so according to that we've got 30 milliamps test current. Now let's just compare that with the meter here. So that one is actually saying 39, so it's not mega accurate, but it gives us an indication. Voltage. Okay, so let's just check the test current again. So that's saying 29 milliamps. And then across the fat strip. So that's saying 1.5. See, .66, and the thin strip, I've lost the thin strip again. Right, I had to get a new thin strip, I lost the other one. So that's actually saying 2.058, which is obviously out of range a little bit, so we'll move that up to the next, times 10. Okay, saying $300. Yeah, so again, this one doesn't. Yeah, it doesn't really like working below 300 millivolts, even this one, which is very peculiar. It must be a thing with these voltage meters. So if we just increase the test current. So it's on 30. So I'm 43 now. So that's basically saying 0.5 of a volt. And if I click that on, well, keep losing everything. Oh, here's the clip. Let's just check the actual voltage coming in. So we've got 40 millivolts coming in. We've got 380 coming out. So yeah, this one, so as long as it's above 300, it seems to be more accurate than the other one, but they don't like going below 300. Yeah, below 300 it just stops working. I have decided to end the video at this point. It's gone on far longer than I had anticipated. I apologise for the length of the video. It wasn't my intention to make it that long, it's just the way it's panned out. I have actually planned another part of the video. I will release that as a separate video and hopefully that will be much shorter, but it is in the same series. It's a follow-up to a follow-up. So again, I do apologise again for the length of that one. Very sorry for that. If you enjoyed this video, please subscribe to the channel, please like the video, and I do appreciate your support. So thanks very much, and I will be releasing the third part of this series pretty soon, so keep an eye out for that one. Coming relatively shortly. I don't know if you recognise this, anyone. I've had this since I think 1989, and the other day it started playing up, so I'm going to do a video on what I did to fix it. The keypad hasn't worked for years. It's a common problem on these. There's a ribbon cable that just breaks off the back. I'm possibly going to look into making an alternative panel for this, but it would have to be separate. Anyway, look out for that video. It'll be coming soon.